A polynomial in one variable has the form that's listed right here, where the a's are coefficients, which represent numbers, and then we have x's to integer powers, and the integers have to be non-negative. So maybe just to list out a couple of examples of polynomials would be something like 5x to the fifth minus 3x cubed plus 2x squared minus x plus 1. So here's an example of a polynomial. Notice that I don't have an x to the fourth, but that's okay. You just have to have x's to add positive integer powers multiplied by coefficients and perhaps just a number at the very end. Your polynomial could be much simpler or it could be much more complicated. So like a simpler one would be something like 100x to the 12th. So just that itself is a polynomial. And maybe just a couple of others. You could have negative 0.1 x to the 51st minus x to the 21st. So here are three examples of polynomials. One other portion of the definition is something called the degree, n, and that refers to the largest exponent that appears within your expression when the expression is expanded, when it's multiplied out, like there's no parentheses at all. So if we look at these three polynomials, I would just like to jot down what is the degree of each of these. So the degree of this polynomial would be 5 because that's the largest exponent that appears within the expression. If I look at our second example, it's 12. And for the last example, the largest exponent is a 51. This whole thing is expanded, so the degree is 51. It might be useful to look at things that are not polynomials, so I'll just list a couple of examples. So we could have something like 15x to the fourth minus 2x squared. So far so good, but I'll put a plus the square root of x at the end. So this does not fall under this definition here. So here we have x's to powers and nowhere is there a square root. Something else that could go wrong would be if we had something like, 1/2 the absolute value of x minus x to the 7th plus 3. This is also not a polynomial, and that's because of the absolute value. Again, that does not appear within this expression. And maybe one last example of something that is not a polynomial would be something like if we had, let's say, 12x to the negative 2 plus 5x to the third. The problem here is that we have a negative exponent, and we never have a negative exponent appearing within this definition. So none of these are polynomials, all of these are. For the rest of the lesson, what I want to focus on is how do we add, subtract, and multiply these types of expressions together? Let's check out example 1, where I first want to add a couple of polynomials, and then I would like to subtract a couple, just to see what that looks like. So here I have a polynomial of degree 6, and I'm adding it to a polynomial of degree 4. Since we're adding these two things together, essentially all we're going to do is combine like terms. So I'll try to keep this very systematic, but what I'm going to do is start with the x to the 6th and see if that ever happens again. Do I have another x to the 6th anywhere in this expression? I don't see another one, so I know I have a 5x to the 6th that appears in my answer. Okay, I think I'll maybe drop down to an x to the 5th to see if that ever appears. I don't see one. All right, so now let's focus on x to the 4th. There are 4x to the 4ths right here. That is the only one, so I'm just going to copy that down. So far, nothing has happened by adding these two together. Now, what about an x to the power of 3? So here I have a 3x cubed and a 7x cubed. And essentially, all we're going to do is just add the two coefficients together. I have 3 of one, 7 of the other, so we have a total of 10x cubed. Okay, continuing, for x squareds, I have negative 2x squared and a 5x squared. If I combine those coefficients, I get 3x squared. Okay, now I have x to the first power, and this is the only one, so I'll just put a plus x. And then I have negative 7 and positive 1, which adds to a negative 6. And this is my answer. So I've combined all like terms, and basically I've added these two polynomials together. Now, what if we were to subtract polynomials? So I have this polynomial of degree 4, and I'm subtracting another polynomial of degree 4 from it. What I'm going to do is distribute this negative into the parentheses. In fact, I don't even need the parentheses on this very first polynomial, so I'm just going to copy this entire problem down again, but I'm going to distribute this negative to every single term in the parentheses. What that will do for us is change the sign on every single number. So it'll be negative, positive, negative, negative, negative. So let's rewrite the question. This is negative x to the fourth plus 10x cubed plus 0.5x. Then we're going to have minus 4x to the fourth plus 7x cubed minus 8x squared minus 1.5x minus 6. And now I can combine like terms just like I did in the previous question. So let's see. I'll start with the x to the fourth. We have one here and one here. So that's a negative x to the fourth minus 4x to the fourth. That's negative 5x to the fourth. I'll now focus on the x cubes. So I have one here and one here. I have 10 and 7, so that's a total of 17x cubed. All right, I guess x squared would be the next one. I only see one right here, so it's going to be minus 8x squared. Okay, now I have x to the power of 1. There's 0.5 here, and there's negative 1.5 here. If I take 0.5 and I subtract 1.5, I'm left with minus 1x. So I'm just going to write that as minus x. You could put a negative 1 in front of it if you wanted to, but that's the same thing as what I wrote. And then the last thing is going to be a minus 6 at the end. And here we go. This is the answer, and this is how you would subtract two polynomials. You would just distribute the negative into the parentheses and combine like terms. So adding and subtracting is very straightforward, and multiplication isn't too much more complicated. All we're going to do is use the distributive property. So I wrote that up here. We've used it before. Essentially, you can take a value and multiply it to every single term that appears within the parentheses. The trick is, if we start with 3x plus 1 times 4x minus 7, we're going to use the distributive property on 3x, so multiply that to every single term in the parentheses, and then continue this process for this term right here. This one gets multiplied in as well. So essentially, we're using the distributive property 2 times. What this will look like is the 3x gets multiplied to both terms. Then this plus 1 will get multiplied to both terms as well. Okay, if I write this out, I'm going to start with the 3x. So I have 3x times 4x. Then I have minus 3x times 7. When I distribute in the 1, that's really not going to do anything, but just to write it out carefully, we're going to have 1 times 4x minus 1 times 7. The last thing to do is use some properties of exponents and combine like terms. So let's see, we have 3x times 4x, that's 12x squared. Then I have minus 21x. Then I have plus 4x minus 7. And the only like terms are the two middle terms. So that's 12x squared. We have a negative 21x and a plus 4x. That is negative 17x minus 7 at the end, and this is the final answer. So essentially, what you have to do is use the distributive property, but on everything that appears in this first set of parentheses. So let's try that with something just a little bit more complicated. So same idea. I want to multiply 2x squared plus 1 into this set of parentheses. I'm going to multiply the 2x squared to every single term, and then I'm going to do the same thing with this plus 1. So I'm going to try to write this out carefully, but 2x gets multiplied to everything. And then the 1 gets multiplied to everything as well. Here's what we have. This is going to get kind of lengthy, so I'm going to write this in a couple of lines. My first line is going to be what I get when I multiply in 2x squared. And I'm going to skip this first step. I'm really going to start at the second step here where I can do 2x squared times 4x cubed in my head, So that's the answer I'm going to put right here. 2 times 4 is 8. X squared times x cubed is x to the 5th. That's the first term, 8x to the 5th. I then multiply 2x squared to 2x squared. So 2 times 2 is 4. And x squared times x squared is x to the 4th. I'm just adding the exponents. Okay, then I have 2x squared times a negative x. So I get negative 2x to the power of 3. Again, I'm adding the exponents. And then the last one is 2x squared times 1, and that simply is just 2x squared. All right, directly below this, I'm going to now distribute in the 1, and I'm going to write that down here. And I'm going to be a little bit careful about this too, where I'm actually going to line up the like terms. So if I distribute this 1 in, I'm going to get a 4x cubed. Why don't I write that below the x cubes? That way when I combine like terms, it'll be easier to see. So if I multiply everything by 1, that's going to be very easy. 1 times 4x cubed is just plus 4x cubed. 1 times 2x squared is plus 2x squared. 1 times a negative x is negative x, and 1 times 1 is 1. So essentially what I am doing at this point is I'm taking all of this and adding it together. And I've lined it up so I have a couple of like terms that I can combine in the middle. So we're going to have a lengthy final answer, but we have 8x to the 5th plus 4x to the 4th. Okay, I have negative 2x cubed plus 4x cubed. That's a positive 2x cubed. Then I have 2x squared plus 2x squared. That is plus 4x squared. Then I have minus x and plus 1. And this is my final answer.